Hello, I'm Clay Shears. Welcome to Part 3 of the Introduction to Parallel Programming course. This module is Implementing Domain Decompositions with OpenMP. The objectives for this module are to be able to identify for loops that can be executed in parallel, identify blocks of code that are also suitable for parallel execution, add the OpenMP Pragmas that will allow you to execute these for loops in parallel, and demonstrate the proper use of the single and the no-wait clauses within OpenMP. What is OpenMP? Well, OpenMP is an API for parallel programming. It was first introduced in November of 1997 by the OpenMP Architecture Board and has now become a standard for threaded and shared memory programming. It's a set of compiler directives, library functions, and environment variables. But it's not a language. It's actually attached to a language like C, C++, or Fortran. It's also, the parallelism is based on the fork-join model that we discussed in Part 2. OpenMP is well suited for domain decomposition problems. It's also available on multiple operating systems like Linux, Unix, OS X, and Windows. It's the compiler that is going to define whether or not you are able to write programs in OpenMP. Some of the weaknesses of OpenMP is that it's not well tailored for task decomposition problems. The compilers that support OpenMP don't do any error checks for you for race conditions, deadlocks, or other threading errors. Pragmas are handled by the preprocessor. When the preprocessor finds an OpenMP Pragma, it will then insert code that implements the threading that is defined by that Pragma. All OpenMP Pragmas start with the same syntax: pound Pragma, OMP, and then the rest of the Pragma. Now, of course, Pragmas have to appear immediately before the relevant construct to make sure that the code that is being influenced by that Pragma is easily known. Pragmas will affect a single statement. If you need for the Pragma to extend across multiple statements, you need to enclose those statements within curly braces. The compiler directive, pound Pragma OMP parallel for, instructs the preprocessor to take the following for loop and divide up the iterations and assign those blocks of iterations to different threads. The number of iterations within that loop must be computable at runtime. Loops must not contain a break, a return, or an exit statement. And loops must not contain a goto that has a label outside of the loop. To be valid, the block of statements that are affected by an OpenMP Pragma must have a single entry point and a single exit point. Here's an example loop and the OpenMP Pragma that will parallelize that loop. In this case, I will go from first to size and increment itself by prime. To be a valid OpenMP loop, each of those values must be assigned a value at the time that this part of the code is encountered by the execution. At the end of each parallel for, there is an implicit barrier synchronization. That means that all threads are going to meet at the join point and wait until all threads have finished before proceeding with the main thread. This is to make sure that the parallel code is sequentially consistent. If you're running the code sequentially, of course, those loops are executed one iteration at a time, and only when the last iteration is completed does the code proceed to the next part of the execution. Therefore, OpenMP enforces an implicit barrier, which is an implicit join of all threads at the end of the parallel region defined by the parallel for Pragma. There may be cases where you'll have nested loops. For example, this code shows Floyd's algorithm to compute all pairs' shortest paths within a graph. It has three nested loops, K loop being the outer loop, the I loop being the middle loop, and the J loop being the inner loop. You can only add one Pragma to any one loop, so you have to decide which loop is going to give you the best performance when you make it parallel. In this case, if you examine the code, we can see that both the J loop and the I loop can be made parallel because of the computations that are inside the inner body of the J loop. The K loop cannot be made parallel because it acts more like a time series sequence, which has to be executed in serial for the algorithm to work correctly. Now, which would you choose if you had to choose whether you're going to make the J loop or the I loop parallel? Well, if you examine the code, you'll notice that the J loop runs from 0 to n. The I loop also runs from 0 to n. If we make the J loop parallel, we only get n executions that can be done in parallel. If we make the I loop parallel by putting the Pragma outside of that, we actually get n squared computations that can be divided up amongst threads and made to run in parallel. So the I loop is the better choice to make parallel because it has more operations that can be divided up amongst threads than using the inner J loop. The amount of work that we have that can be divided up amongst the threads in parallel is also known as grain size. We looked at this in the previous slide by trying to decide whether to parallelize the J loop or the I loop. Of course, we saw that the I loop actually has more computations involved in it than just the J loop. One other point, every time the execution encounters an OMP parallel pragma, it creates a fork join within the code. And so there's overhead in forking off the threads and joining those threads. So one thing that I want to do if I want to improve my performance is to reduce the number of forks and joins. Again, from the previous slide, if I'd put in the OpenMP pragma at the J loop, I would have many more fork joins than if I put the OpenMP pragma on the I loop. Here we see the Floyd's algorithm triply nested loop with the added OpenMP pragma on the I loop. We're almost there, but not quite, because we have a problem with the J variable now. J is going to be a shared variable by default, and in fact, all variables are shared by default within OpenMP, except for the for loop iterator variable that is being used for the OpenMP pragma, in this case the I loop variable. But J will be used as a shared variable, and we don't want that to happen because in that case we'll have threads stepping on each other's values of J and getting the wrong computations. So how can we fix that? One way to fix that is to make J private. And the way that we can make J private the easiest is to add a clause that tells which variables we want to have private within our parallel regions. So we see in this example where we've added the private J clause to make sure that each thread gets a copy of the variable J. The private clause ensures that every thread gets its own copy of the variable J. With respect to private variables, if each thread has its own private variable, the shared copy of that variable is unreachable. If we create a private version of a variable, then the shared version of that variable is no longer accessible during the execution of that parallel region. So no thread can actually access a previous copy of a variable J in our code, and no thread can assign a new value to the shared J during the execution of the parallel region. One other restriction on private variables within OpenMP is that they are undefined when they enter the parallel region. So the first thing that your code must do within a parallel region is give a value to a private variable before it's used in any other way. At the end of a parallel region which has private variables defined, those variables will go away at the join of that parallel region. So all the values of private variables computed inside that parallel region will be lost. Here's another example of a loop code. In this case, we run a variable I from 1 to n. We calculate the division of two corresponding elements out of a vectors a and b, assign that value into temp, and then take and square that value and store that product result into the corresponding element of C. Now this seems perfectly parallelizable except for the value temp, which is being used in this code. The temp variable is a dependence that we have between iterations of the loop, which will actually prevent us from making this a parallel loop. Fortunately, OpenMP has a solution. The solution is to make temp a private variable so that each thread has its own copy of the temp variable. And then when the iterations are divided amongst the threads, each thread will have its own copy of temp that it can be used to compute with. Thus, we've eliminated the dependence on the variable temp. A variation of the private clause is the first private clause. In this case, each thread will get its own copy of the listed variables, but those variables will be initialized with the value of the shared copy at the time that the parallel region executes. Now this value is going to be assigned once per thread and not once per iteration. The first for loop here will assign values into the A array. The first private clause on the second loop and the OpenMP pragma there will give each thread a copy of the A array, assigned all of the values that were given to that A array elements in the previous for loop. Those elements are updated as we see in the loop, but like the private clause, all of those updates will be thrown away at the end of the parallel region. With the last private clause, at the end of the parallel region, the value that would have been assigned to the shared variable last, or in the last iteration, is assigned into the shared variable and carried outside of the parallel region to be used external to that parallel region. Now it doesn't matter which thread is actually assigned the last iteration of the loop, or which thread actually executes last, whether it's the last or some other iteration of the loop.